This screencast is on limiting reactants in stoichiometry problems. Now, in our last video on stoichiometry, we talked about s'more making and how the reaction, if you will, for a perfect s'more was 2 graham crackers, 3 chocolate pieces, a roasted marshmallow to make a perfect s'more. And that if we wanted to write that as a chemical reaction, we'd have 2 of the graham cracker squares, 3 of CH for chocolate pieces, 1 M for marshmallow, and then that made 1 G2 CH3M could be the formula of the s'more. And so I wonder if you've ever been to a bonfire and maybe someone showed up with a box of graham crackers and someone with a package of chocolate and someone with a bag of marshmallows. Do you know what will run out first? Well, limiting reactants is the idea of calculating that. What reactant or what food ingredient here is going to run out first when we try to make s'mores? To figure that out, we need to calculate just how many s'mores, just how many G2CH3Ms can we make from each of our reactants. We do 3 separate calculations. So let's start with the graham crackers. They come in sheets like this, and I have a box at home. The box says it's got 13 servings, and it also says that a serving is 2 of these sheets. Now, each of these sheets has 2 G's on it, but again, it says that a serving is equal to 2 of these full sheets. Okay, so that's some quantities that I'll need in my first problem. So I start with what I know I have. My known is that I've got 1 box of graham crackers. I'm going to put that known over 1 just so I don't accidentally put anything else in that denominator. I'm going to do unit conversions. I'm going to bring down my unit box. Well, what do I know about a box of graham crackers? The only thing I know about that box is that it has 13 of those servings. Well, what do we know about serving? Bring down servings. I know that every 1 serving has 2 sheets. Well, get rid of sheets. I'm trying to get all the way to s'mores, to G2CH3M. Well, I know that every 1 sheet has 2 G's. Oh, now I'm getting somewhere because if I bring down G, I know how many G's are in a s'more. For every s'more, there are 2 G's in 1 s'more. I need 2 of the graham cracker squares to make every 1 s'more. And so I've gotten rid of the units box, the servings, sheets, and G to get to my s'more, or how many of the product I can make. These 2's actually cancel, and so then we just are left with 13 times 2 is 26 s'mores can be made from the graham crackers. So then I go to the chocolate bars. I need to repeat this process for the chocolate. And there are 6 full-size chocolate bars in the package, and each one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 CHs in 1 bar. So there are 12 of those chocolate pieces in each bar. So what do I know? What am I starting with? Well, I know that someone brought 1 package of chocolate to the bonfire. I know something about the packages. Oh yes, that there are in every 1 package 6 bars of chocolate. And then what do I know about the chocolate bars? That they contain 12 CHs in every 1 bar. And I know from CHs how to make my s'mores. I know that 1 s'more needs 3 of those chocolate pieces. And so then I'm going to be able to make 24 G2CH3 or s'mores from the chocolate. All right, and last is my marshmallows. My marshmallow bag says that there are 12 servings in the bag. I have a bag of marshmallows at home. It also says that a serving is 4 pieces, so 4 marshmallows. Now I know someone brought one bag. What do I know about the bag? That it contains 12 servings in every bag. What do I know about a serving? Well, every one serving is 4 marshmallows. And I know how many marshmallows are in my s'more. A s'more just needs 1 marshmallow. So bags cancel and servings and marshmallows. And wow, from the marshmallows, I can make 48 of the s'mores. Now, in a limiting reactant problem, we can only make as much s'more as the limiting reactant allows us to make. So the point is, when we're analyzing this, we ask ourselves, can we make 26 s'mores? Can we make 24 s'mores? Can we make 48 s'mores? Well, we can only make 24 s'mores because at that point, once we made the 24th s'more, we are out of chocolate. And so the way I like to make s'mores, you usually run out of chocolate first. So we'd say that all we can make are 24 s'mores, and that the limiting reactant then is the chocolate. It's the one that will run out first. So the limiting reactant is chocolate, and it's going to limit us to only being able to make 24 s'mores. We'll never be able to make the 26 or the 48 s'mores. So in limiting reactant problems, we're going to pick the least amount of product, and that's how much product we'll be able to make. So just to review, what's a limiting reactant? The reactant that runs out. It's going to cause the reaction to stop. And so in our example, the chocolate was limiting. Once it runs out, we have to stop making s'mores. Graham crackers and marshmallows were both present in excess. Once even one reactant runs out, the reaction stops because it can't make any more of the product. So let's look at some chemistry examples. Now, in our examples, we're always going to do as many stoichiometry problems as we have reactants with given known quantities that could potentially be limiting us. Now, if it says something is present in excess, that's not limiting us, so we don't have to worry about that at all. But we'll do a stoichiometry problem for each known that could be limiting us, that we're given a value for. So this problem says how many moles of water is produced when 2.3 moles of O2, there's one known, and 2.3 moles of H2 react. So we have two known given values. 2.3 moles O2 is one known. The other known is 2.3 moles of H2. Now it says how many moles of water is produced. This is just a mole to mole problem. How do we get from moles of one compound to moles of another? Well, we need the balanced equation. So the way that we're going to get there is we're going to use the coefficients from the balanced equation. So in the first problem, let's bring down moles of O2, and we want to get to moles of water. So we look for the coefficient. 2 moles of water are produced when that's an implied 1 mole of O2 reacts. And so we just get 4.6 moles of water are produced from the oxygen. Now we're going to do the same thing for hydrogen. Bring down moles of hydrogen. We want to know how many moles of water can be produced. We know it's for hydrogen, it's 2 to 2. Okay, well those 2's actually just cancel, and so 2.3 moles of water can be produced from the hydrogen. Now here's the thing with stoichiometry problems, we can only make the lesser amount. With our limiting reactant problems, we can only ever make the 2.3 moles of water. At that point, we will run out of hydrogen. So hydrogen is our limiting reactant. So hydrogen is our limiting reactant. It allows us to only be able to produce 2.3 moles of water. Sometimes folks mistakenly add up these two values, or they subtract them, or they do some calculation. But all we're doing is picking the smaller one and ignoring any larger values. We can only make the lesser amount in a limiting problem. Next, we're going to do another limiting reactant problem. In this problem, it says if you have 7.5 grams of NaOH and 10.5 grams of barium chloride, how many grams of sodium chloride is produced? So again, we have two knowns, 7.5 grams of sodium hydroxide, 10.5 grams of barium chloride, but this time we've been given grams of reactant and asked to get to grams of product. So here we're going to do a gram to gram problem. So we'll write down our two knowns. And put them over 1. And then we'll have to bring down grams of sodium hydroxide and try to get to moles of sodium hydroxide. First, just getting rid of grams and getting to moles, so that then we'll be able to do a mole to mole conversion to get to sodium chloride. So let's start off with the molar mass of sodium hydroxide. Sodium is 22.99. Oxygen 15.999, hydrogen 1.0079, and we can add those all up and get 39.9969. That's grams per mole. So the 39.9969 are the grams that are in every 1 mole. Now we'll bring down moles of NaOH because we want to get to moles of sodium chloride. That's our desired compound, is sodium chloride. And so we'll look at the coefficients. We'll go to the balanced equation and say 2 moles of sodium chloride are produced for every 2 moles of sodium hydroxide that react. And lastly, we don't want moles of sodium chloride. We would like to be in grams of sodium chloride. So let's figure out the molar mass of sodium chloride. We'll add up a sodium and chlorine and get 58.443 grams per 1 mole. So in every 1 mole, there are 58.443 grams of sodium chloride. Moles cancel, and we need to multiply that all out, and we get 11 grams, if we round up, of sodium chloride are produced. Now we need to do the same thing, but for barium chloride. Bring down grams of barium chloride. We first need to convert that to moles of barium chloride. So we'll add up its molar mass. We have just 1 barium, but 2 chlorines. double the chlorine mass for about 70. We'll add these up for a molar mass of 208.233 grams every 1 mole. So we'll put our 208 in the denominator here with grams, or in every 1 mole. We're going to bring down moles of barium chloride. We don't want to be in barium chloride. We want to be in sodium chloride. And again, 2 moles of sodium chloride are produced, but when every 1 mole of barium chloride reacts. Cross out moles of barium chloride. The last step is to bring down moles of sodium chloride and get to grams of sodium chloride. And that was the same as our last step above. Same molar mass. So this final step looks the same when we want to get to grams of sodium chloride. So we'll multiply that out and get 5.9 grams of sodium chloride. Now in our limiting reactant problems, we can only ever make the lesser amount of product. So we can only make 5.9 grams of sodium chloride. At that point, we run out of the limiting reactant, which is the barium chloride. So we can't make the 11 grams. This reaction can produce 5.9 grams of sodium chloride. And barium chloride is the limiting reagent. That's our limiting reactant. It limits us to only being able to produce 5.9 grams of sodium chloride. I want to point out one last important point in this problem, and that is that the limiting reactant is not necessarily the reactant that is present in the lesser amount. You just can't tell from the starting amounts of reactants how much product they'll produce because of the different molar masses of the various reactants and products. If we look at our reaction, we actually started off with 7.5 grams of sodium hydroxide and 10.5 grams of barium chloride. Now, even though we started off with less sodium hydroxide, that wasn't the limiting reactant. Actually, the barium chloride was the limiting reactant. So even though we started off with 10.5 grams of barium chloride, that actually limited us to only being able to produce 5.9 grams of sodium chloride. So sometimes folks mistakenly think that the limiting reactant is the one that there is less of, the 7.5, but that's just not necessarily true. You have to do the calculations to figure out which reactant actually produces the least amount of product. And in our case, that was barium chloride in this example. So barium chloride is limiting, even though at the start of the reaction, there's actually more barium chloride than sodium hydroxide. So now you know how to do limiting reactant problems that are both mole to mole and that are gram to gram.